Good evening, everybody. Thank you for coming out tonight. We know there's a lot of other things going on in town, so it's great you were able to come. I'm Tom Reby. I'm chair of the J. Robert Oppenheimer Memorial Committee, and I want to welcome Dr. Feryal Özel tonight and welcome all of you to the 49th Annual J. Robert Oppenheimer Memorial Lecture. We've missed the last 2 years because of the coronavirus. And we want to dedicate tonight's lecture to the memory of J. Arthur Freed, who was a member of our committee for 49 years. As our founding committee members have faded away, we have a new generation of members who have taken up our work with enthusiasm. I thank the 21 members of the Oppenheimer Committee who have worked incredibly hard to celebrate our 50th anniversary. Our committee began in 1971 when John Brawley realized more needed to be done to honor J. Robert Oppenheimer, the founder of modern Los Alamos. Oppenheimer had been humiliated by the right during the McCarthy era in Washington. His security clearance was revoked on contrived charges, and he was forced to defend himself after leading the Manhattan Project, one of the greatest scientific and national security achievements of our time. Under Mary Lou Williams and others, our committee worked for years to have Oppenheimer's security clearance reinstated. 2 days ago, we learned that 44 US senators from both parties wrote to Secretary of Energy Jennifer Granholm asking her to vacate the revocation of Oppenheimer's security clearance. Aside from these lectures, our committee provides scholarships for promising students from local high schools. Since our scholarship program began in 1984, we have granted $668,000 to 264 students. Some of these students will be the first in their families to attend college. We also support other science events in the community, and we welcome your financial support of our scholarship efforts. So let's recognize this year's scholarship winners. If you're here, please stand up when your name is called. From Capitol High School, Rhiannon Velarde. Amy Segura. From Santa Fe High, Isabella Garcia. From Pewaukee High, Mateus Matas. Christian Holgan. Deshaun Sanchez. And from Los Alamos High School, Aaron Phillip. Xin-Yong Huang. Philip Ionkov. Olivia Koo. Christina Nosili. And Jennifer Gao. Thank you. So why are we all sitting right here tonight? Why is Los Alamos here? Let's look back to 1922, when a young Robert Oppenheimer was emerging from high school in New York City in frail health. His parents thought some good outdoor time out west would restore him, so they hired Herbert Smith from the Ethical Culture School to take him outdoors. By a simple twist of fate, Smith chose the Sangre de Cristo Mountains of New Mexico for Oppenheimer's rehabilitation. Robert Oppenheimer immediately fell in love with New Mexico and started spending his summers riding his horse all over the region, including this Pajarito Plateau. He bought 40 acres and a cabin on Grass Mountain in the Pecos and spent as much time as he could spare in the mountains. He always said he had two great loves. One was physics and the other was New Mexico. When it came time to launch the Manhattan Project, the government looked to the southwest for a remote site. After rejecting Jemez Springs, Oppenheimer suggested the site of the Los Alamos Ranch School. General Leslie Groves immediately approved, and the rest is history, as they say. Years later, Oppenheimer said, "I am responsible for ruining a beautiful place." Because of Herbert Smith and J. Robert Oppenheimer, we are all sitting here tonight. What is your story, and how does it wind back to J. Robert Oppenheimer? I want to introduce Oppenheimer committee member Galen Geisler to introduce our speaker. Thank you very much.
Thank you, Tom. What an exciting time for students of the cosmos. We have the James Webb Space Telescope. You've seen some images here. New results almost every day from Mars and other planets, and world-changing astrophysical discoveries nearly every year. Coinciding with the centenary of Einstein's theory of general relativity only 7 years ago, we saw the first detection of gravitational waves. Equally groundbreaking and connecting even more intimately with Einstein's theory are the first ever images of black holes, brought to us in no small part by tonight's speaker. We will hear from a founding member of the Event Horizon Telescope, the Earth-spanning instrument that gave us the donut-like images of massive black holes in our own Milky Way and in M87, the giant elliptical galaxy at the heart of the Virgo cluster. It is my great privilege to introduce this year's Oppenheimer Memorial Lecturer. Professor Feryal Özel comes to us originally from Istanbul via degrees at Columbia and Harvard. She has been a professor at the University of Arizona's Astronomy Department since 2005 and happens to be stopping in Los Alamos on her way to Georgia Tech to be chair of the School of Physics there. She's received a Guggenheim Fellowship and many other awards. Some of them are listed in your program. Please join me in welcoming Feryal Özel to present Black Holes from Oppenheimer's Ideas to the first direct images.
It's my absolute pleasure to be giving you this Oppenheimer Memorial Lecture. I love Los Alamos. I've spent some time here, not as much as I would have enjoyed, but I'm very happy to be here tonight to tell you about the images of black holes and how our understanding evolved from Oppenheimer's times and even earlier to the Event Horizon Telescope results that I'm going to share with you this evening. This is the Milky Way Galaxy, our own galaxy, what we see if we stare in the sky, especially in the summer. And at the heart of it is a black hole that we call Sagittarius A star. It is about 4 million solar masses and one of the primary targets of our imaging experiment that has been going on for about 20 years. And what we did was put together an Earth-sized array, as Galen was mentioning, literally telescopes on every continent that are capable of observing in the millimeter wavelength of light, and spanning north to south from the almost North Pole, Greenland, to the South Pole, and this telescope array in Hawaii, and turn them to the center of our galaxy, looking through all of these gas clouds and dust and all sorts of effects through the disk of our galaxy to where we thought this 4 million solar mass black hole was. And we obtained the image that we shared with you just a couple of months ago in May. But I think I'm getting ahead of myself, so I'm going to rewind and tell you a little bit about what black holes are, why we wanted to image them, and take even a further step back and tell you about Einstein. That's where all of this is going to start, but there is a long journey, both in terms of our understanding of black holes and its theoretical properties, and in terms of developing the right hardware and the collaboration to be able to image them, and then merging the two to tell you about the properties of black holes. So let's start at the very beginning, which is the Einstein's theory of gravity. Prior to Einstein, we've used a theory of gravity that is due to Newton, and it got most everything right. It was formulated as a force between objects, and it got everything right until it started not getting things right, like the precession of Mercury's orbit and a couple other phenomena. So here comes Einstein in 1915 and comes up with a completely different formulation of why massive bodies attract one another, or what we think is an attractive force between them. It's a geometrical theory. It completely rewrites how we think about physics. And what it says is that gravitational bodies actually curve the space-time around them. This is our sun. The fabric of space-time is represented here with that grid. And as you can see, there is a little bit of a dent in that grid. That is caused, of course, this is our poor attempt maybe, at trying to take something that's in 4 dimensions and represent it in 2 dimensions. So imagine a fabric that is this grid, and a massive object like our sun creates a curvature in it. That's part 1 of the theory. Very elegant formulation, simple equation as you see on the right. But then there's another part that says, and all other bodies follow straight paths in this curved space-time, including light. So that's what you're seeing here, the 2 paths of stars, one the path that would have been, that light would have followed if the sun wasn't there, and the path that it follows when the sun is there, going in and out of that curved space and looking to a distant observer as if it was some other place. This was the original confirmation of Einstein's theory. It predicted that shift in the position of stars correctly, and it gave us a completely new way of understanding gravity and the universe. However, Einstein's theory also had what a physicist would call problems. One aspect of the theory is that it predicts singularities and what we call event horizons, or points of no return. So let's take the same fabric of space-time, and let's take a whole bunch of light rays coming from the right side of the screen, presumably traveling in straight lines, and look at what would happen if we, instead of the sun, put in a massive object that curved it so much that it actually trapped some of the light in it. So it's just an extreme warping that you could achieve if you could pack enough mass into a small enough volume. Einstein's theory allowed it, and not only did it allow it, but that was actually the first solution of that elegant equation that I showed you previously. Shortly after the formulation of the theory, Schwarzschild, during World War I, actually said, this is an allowed solution of the theory. And people hated it. They hated the fact that there is an infinite energy density that is allowed at the center, and that it is predicting basically the presence of that point of no return where even light is trapped, and it is cut off from the rest of the universe as far as information is concerned. But wait, there is more. There are other problems with the theory, or with the prediction of black holes. I listed just a few, some that we still grapple with and some that we have solved. The first one, and the one that really boggled the physicists' minds at the time and made Einstein argue tooth and nail against the existence of black holes, is, can a black hole form in the universe? And not only can it form, but can it form in a finite amount of time? Can that collapse actually happen in a finite amount of time as far as a distant observer is concerned? It might sound like a mathematical curiosity, and at the time it was, but it was a big outstanding problem. Are black holes stable? Some members of our audience worked on this problem and laid it to rest. And one that we still grapple with, and string theory is trying to solve, what happens to information crossing the horizon, that point of no return of a black hole? The typical example that we like to give is, you take a laptop hard drive, or you take a piece of coal that is the same mass and throw it into a black hole, and once it crosses the horizon, the fact that one contained terabytes of information and the other practically nothing doesn't matter. The only thing that the black hole cares about is the mass, total mass that goes in. So what happens to that information? Is it lost forever? Is it stored somewhere, etc.? As I said, I'm not going to be able to tell you about all of these answers, but there is one that Oppenheimer laid to rest in his seminal paper in 1939. This is the Oppenheimer-Snyder beautiful work. It is called On Continued Gravitational Contraction, where they showed very elegantly that in the absence of a pressure that is supporting a body, that gravitational contraction would occur it would continue into what we call a black hole solution. And not only that, but it would happen in a finite amount of time. So having answered that first question about whether gravitational collapse can occur and whether it would form a black hole, it's one thing to say, here's the mathematical solution. It's another thing to say, is there a path to getting there? And Oppenheimer, one of Oppenheimer's amazing contributions in the 30s, not counting the Manhattan Project, was, of course, this black hole solution. His is a paper and pencil calculation. However, what I want to show you here is an actual calculation of the dynamics of a stellar cluster that collapses into a black hole. And this is due to thanks to the Illinois relativity group. So again, we're not talking about a single star collapsing into a black hole here. We're talking about a star cluster that is losing support. And what you see is that the horizon is forming, it's growing to encompass everything that is falling in, and that it is happening like nothing is special. This is happening at a finite amount of time. Let's go forward a little bit more. Now that there is more and more support that black holes aren't mathematical curiosities, but perhaps could happen in nature, there is further work on how they would manifest themselves. For example, how much energy would be released if things fell into them, and more importantly, what would their images look like? Now we are coming to the 70s. There's a lot of work in between. In the 60s, the discovery of quasars, the distant black holes that consume a large amount of matter, basically laid the "are there black holes" debate to rest, and the rhetoric switched to okay, what are they like? How do they affect their environment? What do they look like? Can we understand if they are really like predictions of Einstein's theory of relativity, even though he himself, until his death, rejected the existence of black holes? Or are they something else? Is there maybe new physics happening? So the early work on that, I took two examples. I already told you about what we call the Schwarzschild solution that came during World War I. Much later was the Kerr solution, an extension of that singularity with the horizon, not for just the mass of the black hole, but allowing for the fact that the black hole might spin around an axis. Basically, just like every other astronomical body, if it has a little bit of angular momentum, what would happen to the fabric of space-time around it? So I might come back to this term, the Kerr solution of black holes. The Kerr solution was relatively new, and one of the first papers that really explored the properties of Kerr black holes is Bardeen, Press, and Tucholsky. Press being no one other than Bill Press sitting in the audience here, your own Bill Press. And that really started formulating what the properties of black holes, like how does the matter follow circular orbits? How does the photon, the light around it, follow orbits? What does the image look like? And the one on the left is from Bardeen in 1973 as a follow-up on that work. And the one on the right is now starting to consider the fact that black holes are not objects that are isolated in space. There are stars around them, there is gravitational pull, and because of that there is what we call an accretion disk formed by the gas that is pulled from those stars and gas clouds falling onto the black hole. And the first solutions of those were being formulated in the 70s. So going from somebody holding a flashlight behind the black hole and very conveniently lighting it up for us, like in that picture, we started going towards more realistic scenarios where there is actually a source of light coming from the gas circling around the black hole. Having said that, the one on the left captures what we were looking for with the Event Horizon Telescope. Basically, as long as there is a source of light that is close enough to the horizon, or actually it ends up being closer to the photon orbit, another important distance from the center of the black hole, where photons can actually complete circular orbits. What you're seeing there captures what a black hole image should look like, as long as there is that source of photons, that light. A dark hole in the center, surrounded by a ring of light that is very bright, very thin, and if there is further source of light, it could actually be a brighter donut than what is shown here. So as you move from that flashlight scenario to a actual accretion disk where gas is falling into the black hole and it's heating up and emitting that light, what you start seeing are more interesting features like, yes, there is that black hole shadow, that hole in the middle that we expect to see because, as I showed you earlier, black hole is really swallowing the light that gets too close, but outside of it, we see some form of a donut. Why is the donut there lopsided? Two reasons. One, it's actually not the right solution for how the gas behaves around a black hole like Sagittarius A star, or the second black hole like M87 in the Virgo cluster. It is not the right way that gas behaves, so it's not really applicable there. The second reason is that in that type of solution, the gas has a pretty significant circular velocity around the black hole. In that picture, it is coming at you on the left side, it is receding from you on the right side, and it's producing what we call the Doppler effect, things coming at us looking brighter and sounding louder than things receding from us. So we just started maybe wrapping our minds around there could be images of black holes if we could find the right target and if we understood where we should look. Then we really moved to the 2000s, and this is some of the early work that I have done on this subject. I mentioned that the luminet solution wasn't for the right type of flow around the black hole. So we started exploring other types of flows that is applicable to Sagittarius A star and M87. And not only did we understand more of what the properties of those flows look like, but we also started understanding more how, if we did take an image, how it would change as a function of the wavelength of light with which we did the observation. So this is a simulation of the work that I have done in the 2000s, but much later with much more sophisticated computing that we started exploring later in that decade. And what you will see is this still here is what the image would look like if we looked at 1 centimeter. And I'm going to change that wavelength of light to go to 1 millimeter. And you will see that that opaque torus around the black hole is going to shrink further and further and further, and it's going to reveal at some point that horizon, that shadow that we are looking for. So that's that first part. And the second part of it is we also know that gas around black holes isn't static. It actually moves and its temperature changes, its magnetic field changes. So all of these things can affect how the image looks from moment to moment, or in this particular case, as the gas takes its time to rotate around the black hole. So we started being able to fine-tune the observational wavelength at which we would see the horizon, that shadow, and also start preparing for scenarios in which, because of the dynamics of that gas, we may not be able to get a clear picture and develop algorithms in order to deal with how to undo those. As I said, this work started in about 99, but continued during my time in Arizona in my group, where we developed new algorithms that not only work on CPUs, but new platforms. It wasn't common, especially in astrophysics when we started in about 2010, to use graphics processor units in order to solve Einstein's equations, let alone any other physics equation. So what we were able to do with that is really model this plasma, this hot, swirling gas around the black hole with higher fidelity, solve Einstein's equations through that plasma with higher fidelity, and make a library of images that would guide both the development and the interpretation of the Event Horizon Telescope observations. So I will show you now a little movie that we took of my, at the time, my graduate student, now an astronomer at Steward Observatory in Arizona. This is CK. That's a remote control device, basically. He's going to run the simulation on a single GPU on his laptop, just as a proof of concept, initializing the simulation. And with his hand, he basically made a hand gesture for all sorts of commands that you could type into a computer, and in real time render millions of rays of light in order to get images very fast, which is what we needed in order to not only model what the gas is doing, but really project that to what the image would be doing. Here there is no gas, this is just solving Einstein's equations. But as I said, we then use these extremely fast algorithms to make the first movies of black hole environments. So let me show you a still from such a movie. This is now the The black hole is at the center in that purple region there. This is that hot swirling gas, just one snapshot of it. And as you can see, we're calculating all of this and then following it to what a distant observer, in this particular case on the upper right side of the screen, what that distant observer would see. And there, hopefully you can make out that there's, again, a shadow surrounded by a bright ring of light, or the donut. Making these algorithms and coupling them to the behavior of the gas allowed us to explore an entire library of scenarios, accounting for things we know, accounting for things we don't know. We can't calculate physics from the physics from first principles, such as some plasma effects, and really explore what our observations might be able to yield for us. Having done all of this, we had to pick targets, and the closest supermassive black hole to the Earth is Sagittarius A star. It is small, on the small side, even though we call it supermassive, meaning it is not just a few times or 10 times or even 50 times the mass of our sun, but somewhere between million to 10 billion times the mass of our sun. And we find these at the centers of pretty much every galaxy that we look at. So these supermassive black holes grow with the galaxy, really have a give and take relationship. And ours is, like I said, on the small side, just 4 million solar masses, but it's closest to us. Our second bright, beautiful black hole was M87, about 1,500 times more massive and 2,000 times further away. So comparable in size, in angular size, if you just put it in the sky. So we said, we got it. These two are our main targets. Let's now build the array and do these observations at the millimeter wavelength of light, where our models tell us we should be able to see down to the horizon. So how big are they, these best targets that I'm telling you about? This is the moon. Do you know how big the moon is in angular size in the sky? Half a degree. Great. Okay, so let's put degree up there, because if you put your thumb at an arm's length and look at the sky, that's about half a degree. That's the moon. It covers the moon. Okay, let's start dividing this, because we have a long ways to go before we get to the size that we are interested in. We divide a degree into 60 arc minutes. We divide that, each of those arc minutes, into 60 arc seconds. Then we divide that into 1,000 milli arc seconds. We divide that into 1,000 micro arc seconds. Now we are 1/100 millionth of a degree in the sky. And Sagittarius star and M87, one of them is about 40 microarc seconds, and the other is about 50 microarc seconds. So, is this realistic? I mean, this donut thing started back then. We said it's the equivalent of putting a donut at the distance of the moon. So basically put it on the surface of the moon, give somebody a little camera and say, go ahead and take a picture. And make sure it shows you all the details, including the hole in the middle. Okay, so if this is our best target, how are we ever going to actually do this? As you, I'm sure, all know, the resolving power of a telescope goes with its diameter. So this is a backyard telescope. That's one of the largest 30-meter class telescopes that we're building today. These are, of course, in the optical wavelength. We want to do this in the millimeter wavelength, which makes the aperture, that's diameter requirement, even worse. So when you go through the calculation and say, okay, tell me what do I need to build? It turns out to be an Earth-sized telescope. And we went to funding agencies, we asked for that money, and they said, no, you can't possibly build an Earth-sized dish. So then we did the next best thing. which is a technique called very long baseline interferometry. Of course, this has a long and glorious past. It was being used at the longer wavelengths, but the whole idea here is that even if you may not be able to build a single dish that is the size of the Earth, what you might be able to do is put telescopes that are separated by the diameter of the Earth and look at a distant black hole, in our case Sagittarius M87, at the same time, observe it as the light from that source reaches these telescopes, not at the same time, of course. Sometimes one has to travel further than the other in order to reach these telescopes, but simultaneously, and record all of the data. Basically, every waveform that is coming in, getting a little distorted by the atmosphere, reaching the telescope. Let's record each and every one of these and time tag it using hydrogen maser clocks. So they have sufficient timing precision to be able to take a millimeter wave, so gigahertz to 130 gigahertz wave that is coming in, and for each peak and trough, say, here is the arrival time. That's a lot of data, a lot of junk data, but it is a lot of data. So you collect all of that, and then you take these hard drives, you take them to the same place on a correlator, you match up the waveforms that arrived at these different telescopes, you look for that time delay, you match them up, and then you don't get the collecting power of a telescope that would have been the size of the Earth, but you get the resolving power of a telescope that is the size of the Earth. Okay? I'll do one more animation on this concept because that's what the Event Horizon Telescope is based on. So let's say that we had two telescopes on these two continents shown by the red dots there, separated by this length L. This would have given us 1 pixel of the image. So the music equivalent of this is that with these pairs of telescopes, we hear one note, and another pair of telescopes gives us another note in the melody, and another pair gives us another note in the melody. So we're trying to fill, if you think of it as music, pretty much all the notes that you can by these combination of telescopes, and if you think of it as image, information in the image by relying on these pairs of telescopes. So if we had only one pair, that would not be an image. That would just give you 1 pixel. Okay, so we rely on the rotation of the Earth. Our observations last of the order of 12 to 16, 17 hours, because not only do we want the Earth to rotate so that more and more telescopes can see the target, but we also want to make sure that as the Earth rotates, the track that they follow fills in more and more of the information that you're seeing on the right. Even with 10 telescopes spanning the globe, like I said, from north to south, east to west, we don't have the full information of the image. We still have some missing notes in there, missing details, and then we rely on our algorithms to fill in that missing information and really understand what that image looks like. So this is the technique, and as we spent more than 10 years putting receivers on each of these telescopes, in some cases putting new dishes on mountaintops, and really trying to grow the information that we are able to obtain for these images. We also grew the collaboration. We started from a handful of people, and just like a global array, we are now a global collaboration spanning about 25 countries. This is from a meeting that we had back in 2018, before COVID, where we were getting ready to publish the first set of papers on this. But of course, even this doesn't do our collaboration any justice. We have grown in the last few years, and we're never all in the same place at the same time. So let me also show you the faces of EHD. This is basically majority of the people working on some aspect of the collaboration. So it's truly a global effort in every sense of the word. In 2017, we had 7 sites ready. So we said, okay, we are ready to launch the first global observations. And we looked at Sagittarius A star, and we looked at M87 during about a 10-day observing campaign between April 5 and 11. And what you're seeing in these pictures is blue skies in a lot of places. Millimeter wavelength is like a short wavelength radio. So you can observe when the sun is up, as long as your telescope isn't distorted by the thermal effects of the sun. But what you can't do is you can't observe when there's a lot of moisture in the atmosphere. So you want clear skies for that reason, not because of optical reasons. As you can see, blue skies in Spain and in Hawaii and in Mexico and in the South Pole, which is almost always dry. And in the Atacama Desert in Chile. So we gathered a bunch of data, 3.5 petabytes in about 5 days of actual observing in that window. And the data volume is so large that there's absolutely no way to transfer it over the internet. So what we do is we crate up all of those hard drives that recorded each waveform and FedEx them, ship them out of the South Pole, wait for the summer to arrive, and take a cargo plane out, and half the data goes to Bonn, Germany, half the data goes to Cambridge, Mass, to Haystack Observatory, and the combined weight of the hard drives is over half a ton. So it's a lot of data to work with, and it goes through several stages. The first one I already described to you, where you match up every telescope pair, and then you fit a solution to it. Each step reduces the data volume by about 1,000. And then the last step is the imaging, and then there is the analysis part. So I want to show you a little bit more about the imaging. I mentioned to you there are still missing pieces of information because of our incomplete coverage, even with all of those telescopes with the spanning globe. So what we do is create possibilities. We say, we have to respect the data that we have, and we have to allow for different ways of filling in the missing information. And as you do that, you see that slight aspects of the image is changing, right? From one frame to the other. Each one of these is a realization of an image that filled in that missing data in a slightly different way. Good news is that there's a lot of commonality between these images, even when you say, okay, I don't know exactly the missing parts, but you're never losing the hole in the middle, you're never losing the donut, but how that brightness changes around the ring is changing, because that's really small scale stuff that you're more sensitive to that missing information. And so we call these reconstructions with different algorithmic parameters. And the entire set of these that we make, many, many, many thousands of these, we call the top set. Okay? So for Sagittarius A star, we did this, and then we grouped all the images, all the possibilities of images that resulted from our data in 4 groups that you see at the bottom. The last group might look like, maybe you lost the hole there. The average images of the 4 clusters of types of reconstructions. But what I want to show you is that let's take those 4 clusters and the average image in the middle, and what we convinced ourselves with 2 years of testing. This is the reason why we published the Sagittarius A star results more than 2 years after M87 results, because of this little dynamic feature of the images and And because of that fourth cluster there, which is about 0.5% of the images among all possibilities. So if you look at cluster 1 versus the average image, cluster 2 versus the average image, cluster 3, and finally cluster 4, what you realize is that they all contain the same information. So there are details that we can't vouch for, but there are basic characteristics of the image that we are able to obtain. Most importantly, the size of the image. Each one is the same size, as you can tell. The donut is the same size. And because the algorithmic choices don't affect the size, as I go there, I want to, especially for the scientists in the audience who have seen the M87 image, and you might talk, but this is the Fourier space coverage of Sagittarius A star on the left. All the data put together, that ringing structure that is basically giving us confidence that it is a ring and it has a finite thickness, that there's a hole in the middle. All sorts of agnostic modeling confirm that, and that is the image that corresponds to that. And in comparison, this is what we had for M87. What you notice here is that I don't have a laser pointer, so I won't be able to show you. If you look at the middle panel here, the x-axis on these plots is how far away the telescopes are from one another. And the farther away they are, the finer detail you can see. The fact that the South Pole telescope can see Sagittarius A star, the center of our galaxy, but it can't see M87, which is towards Virgo, makes the difference in those data. As you can see, the M87 data stops a little bit sooner than the Sagittarius A star data. But these are the two sister donuts, a little different in size as we expected, a little different in thickness, which we can understand, and this is the full picture of where imaging stands right now. Okay, so in the last little part of my talk, I want to now take these images and connect them to, we talked about Einstein, we talked about Oppenheimer, we talked about the 70s imaging, and then the 2000 black hole images were all theoretical, what we expected to see, and now use these images to ask ourselves, have we learned something new that we didn't know before, either about the theory of general relativity, Einstein's theory, or about black holes, or something else. So, in order to test a theory, you can't just work out the predictions of that theory and get an experiment and compare it. You really need also alternatives, because what if the alternatives also make the same prediction that you're seeing? In order to deal with that, what we did was relax a lot of the assumptions of Einstein's formulation of relativity. In these 6 panels, you're seeing 6 different ways of relaxing those assumptions. Top left is Einstein with everything that we know about the gas around it. The second one says, I'm going to take this curve metric and I'm going to parametrically distort it, and I'm going to allow for all sorts of deviations, make bigger black holes, smaller black holes with, I'll say it, but it won't mean a lot to many of you, with different quadrupole moments, and see what those images look like. Do exactly the same thing that we did in those earlier simulations that I showed you and try to predict what those images will look like. Another metric here, SEN, a boson star. A star that doesn't have a horizon, that point of no return. And it's just slightly bigger than that with some contrived physics. I'm sure some people in the audience love them, but sorry about that. Then dilatones and analytic wormholes. And we put the plasma around it. This is some work that I have done with two colleagues. And we said, what would those images look like? And if we have a prediction for Einstein's theory and these alternate predictions, and we now have the actual measurement from our observations, then we may be able to try to separate these alternatives to general relativity. So what we found is that even if Sagittarius A star was not a black hole that is described by the solution to Einstein's theory, that pure solution, it could still show a bright ring surrounding a shadow. So that's not a unique prediction. But what is unique is the size of the ring and the shadow changes if you do anything to the theory. And it changes pretty drastically. You can take something that is size 10 microarcseconds, and by changing one parameter in the metric, you can make it 50 microarcseconds. So that's the key. If we can get a robust measurement of the size of the ring and the shadow, then we are able to distinguish between these possibilities. And that's exactly what we did with Sagittarius A star's image. These are the basically rings that are showing you the size that we measured from Sagittarius A star. And again, for the scientists in the audience, I just want to show you the different ways in which we did it, different imaging algorithms, different plasma algorithms. And these are the, if you wanted to look at the actual distribution over the angular diameter of the shadow, this is what we found. But now what are we going to compare it to? We have a measurement, we have the theory, we have the alternate theories. Well, how are we supposed to know what it should be? Well, this is where prior observations of our galactic center black hole were crucial and very, very helpful. For literally 2 decades, 2 groups, one at UCLA, one at the Max Planck Institute in Germany, followed the orbits of stars around the dynamical center of our galaxy. And by going back every 6 months and getting a snapshot, just like we did for our solar system back in the 1600s, tracing out the motion of planets, and then being able to determine the mass of the sun from that, even if you don't know what is at the center, by following the orbits of stars around the star object, you can say, that's the mass, that's how astronomy works. So that's exactly what they did. These are reconstructed orbits of many stars that orbit around that very center of our galaxy, that faint source that is 4 million solar masses, but certainly doesn't shine like it's 4 million solar masses. And because of that, we knew exactly what to compare this to. We said, if Einstein's formulation is right, and the black hole is described by this Kerr metric, the size of the shadow and the bright ring should be this. If it's not, if it's any of those alternates, it's something different, which we quantified. And we were able to measure and compare these and showed that it is completely consistent with the predictions of the Kerr metric. Again, I will take just a second to show you how consistent, for those who like the details. These are all of these different combinations of how we measured and calibrated the shadow size. And this is about the 10% uncertainty that is coming from the measurement uncertainty in the size of the ring. But as you can see, that that blue band is the prediction from the theory, and those curves are all falling, the peak of those curves are all basically falling on top of that prediction, which says there is really no reason to suspect any deviation from our understanding of gravity. We combined it with the gravitational wave results, which are for much smaller black holes, and of course for systems that are rotating, two black holes rotating, orbiting around one another at a much smaller mass, and then Sagittarius A star with its 4 million solar mass, and M87 with its 6 billion solar mass. And we are now able to look at the mass range of black holes all the way from 10 to about 10 billion, and all of them right now are consistent to the level that our data allow us to make that comparison in different ways. They are consistent with the predictions of GR. So I will leave you with the image and with one last thought. We get asked a lot, was Einstein right? And it depends on what you mean by that question. Is his theory still describing the phenomena that we see in our galaxy and in extreme cases like black holes correctly? Yes, it is. There's no reason to suspect any deviation. And it does look like those singularities are forming, and there's a point of no return, and it's very commonplace in the universe. Every galaxy has not only a supermassive one, but millions of smaller mass black holes. So, in terms of whether that theory is able to describe the universe around us, yes, it is successful. Was Einstein right in his resistance to the existence of black holes? No, he was dead wrong, and it's only because of that we are able to embark on LIGO and Event Horizon Telescope, and pretty soon from space with LISA and who knows what other instrument, and continue to characterize black holes and how they affected the formation of galaxies and stars in the universe. So I will leave you with that thought. Thank you.
Thank you, Feryal. In the tradition of the J. Robert Oppenheimer Memorial Committee, we have a commemorative medallion for you, which was designed by the late Santa Fe artist Una Hanbury. The profile of J. Robert Oppenheimer is adapted from a bust of Oppenheimer that Hanbury executed in 1973. The bust was commissioned by Los Alamos National Laboratory and is on display at the laboratory's Oppenheimer Study Center. A second cast is in the collection of the Smithsonian Institution's National Portrait Gallery in Washington, D.C. The third and final cast, considered the artist's copy, was obtained by the J. Robert Oppenheimer Memorial Committee and is on a long-term loan to the Los Alamos Historical Society Museum. Refreshments out in the hallway off to the left side back there. Thank you for coming.